Hello everyone. I'm going to give some introduction about probabilistic graphical model. I have to say that it's more like introduction from Moon because it's going to be very brief and very high level, but hopefully it built enough background for the later part of the talk. So understanding probabilistic graphical model is important for causal thinking. So why should we care about causal thinking? I'm sure many of you have seen sensational headlines like this. For example, this one is from Business Insider that shows a correlation between amount of chocolate consumption and number of Nobel Prize win by a country. So if a decision maker wants to make a decision based on this correlation, may decide that the entire country should change the diet to chocolate in order to win more Nobel Prize.
Causality is also important in scientific study. For example, consider that we collect a lot of observation and we notice a correlation between presence of yellow finger and lung cancer. If we only focus on correlation and don't without going toward the actual causation, we may infer that the yellow finger may cause lung cancer, while in fact there is underlying cause into both of those, which is the smoking that can cause yellow finger and lung cancer. Um, Causality in terms of scientific study is important for generalizing our finding and fusing information from multiple modalities or multiple types of data. And it's underlying principle of the scientific understanding, as Carl Jung put it in his, this quotation. Um, it's not just about like not mixing correlation and causation. It also causal thinking requires rigorous modeling of the relationship between variables. So let me give you an example. Let's say that we are interested in understanding the efficacy of two treatments, treatment A and treatment B, for kidney disease. And so we have two treatments, A and B, and we want to choose based on which one are doing better in terms of recovery. And we collected some data, and we realized that when we look at the effect of observation, the recovery is shorter in treatment B. Just based on that, we may decide that, okay, treatment B is preferred. And we may go and actually implement it and see no effect. Um, so let's say that we go back and then talk to our clinical collaborator, and he or she may say that, well, did you consider the stone size? Because the stone size is also important. If in fact we break the population into small and large stone sizes, then we may see complete opposite effect. So while in both group, small people, patients with a small stone and large stone, the treatment A is preferred. But when we look at the entire population, the treatment B is preferred. So we may think that like what is actually going on, like why we separate the group based on the stone size. Um, the decision that we have to make is different. So I'll give you 5 seconds to think about it, and hopefully you come up with some hypothesis that why stone size is important. So in fact, the reason it's important is that the stone size is influencing both treatment and recovery size. It's not really causing them, but it is influencing the treatment. So based on the stone size, a doctor may prefer to go for more aggressive or less aggressive treatment, and so may bias the sample size. And it also it biases the recovery. So this is what's called Simpson paradox. And so if I plot it at a continuous domain, it looks like something like this. This is a schematic, of course. So let's say that on the y-axis we have a cholesterol, and on the x-axis we have exercise. So if we look at the scatter plot, based on the relationship between these two random variables, these two observations, we may decide that, oh, there is a positive correlation between cholesterol and exercise. And so if you're lazy like me, and you don't like to exercise so much, you may say that, okay, if I exercise more, my cholesterol will go up. But in fact, the underlying phenomenon in Simpson paradox is that if you break it into different subgroups in here, ages, in fact, the effect is totally reversed. The more exercise that you do, the less cholesterol that you're going to have. So, uh, so the reason I'm showing you this example is that it's important to incorporate different random variables and how they contribute into our observation. And in order to incorporate this, we need to be able to encode the dependencies. And probabilistic graphical model is a very proper way and formal way to do that. So what is this probabilistic graphical model? Probabilistic graphical model is a language and formalism, and also a set of tools that can help us to model the relationship between high-dimensional random variables. So let's say that we want to model the relationship of between a set of friends that John the Baptist has, and we want to see, for example, if John Baptiste sent a message, what would be the behavior of the other people in his population? Here, whether the person sent the message or not can be viewed as a random variables, and the graph of the friendship of over the entire, let's say here, Facebook of John Baptiste would be the probabilistic graphical model. So probabilistic graphical model can be viewed as a graph that relates multiple random variables, and the connection shows the relationship. It's also very important to model uncertainty, and it has been applied in multiple different contexts in the speech recognition, computer vision, and robotics. So, so to put it a little bit in a more formal way, so let's assume that we are interested in modeling the the world of cellular transduction, and we have several receptors and set of mechanism inside of a cell that eventually translate into the presence or absence or increase or reduction in abundance of expression of the genes. Um, Probabilistic graphical model is a way to formalize the relationship between these variables. So in this case, we have 8 random variables, and from causal point of view, we have multiple layers of influence of set of receptors, for example, the level 1, which is on a membrane, and the second level, which is on a cell level, and finally on a gene level. And probabilistic graphical model can be viewed as a way to encode this relationship. How, for example, receptor B is influencing cytosol inside, and then how those translate into expression of the genes. To put it a little bit more formally, we usually represent directed graphical model because as a set of node and edges. In this talk, I'm not going to talk about undirected graphical model because here we want to focus mostly on causality, and directed graphical model is more appropriate, at least in this context and given the short time that we have. But the way that we represent it is that each random variable can be viewed as a node, and an edge represents the influence or dependencies. So let me give you an example. Let's say that we have two random variables, x and y. Absence of the edge indicate that those two random variables are independent, meaning that the joint density between them can be fully factorized into the marginals, while presence of the node and presence of an arrow between them represent that they are related. We will go over this more detail toward as we progress in the talk. But what is more informative in the probabilistic graphical model is absence of the edge rather than presence of the edge. So in fact, there is a one-to-one correspondence between the structure of the graph and set of independence that you can read from the graph. So here in this example, when there is no edge between two random variables, that indicates that two random variables are independent, while when there is an edge, it means that we cannot infer that they are independent. So the general rule is that they can be dependent on each other. One can view also the graph as a generating procedure. So here in this example, let's say that we have 6 random variable x1, x2, x3, x4, and x5. Sorry, 5 random variables. So the observation that we have is 5-dimensional. So one can view probabilistic graphical model as a way to create this 5-dimensional distribution. So how, if I want to draw the sample from this probability density, one way to view it is that first I generate sample from x1. So that would be from x1. And then I create x2 based on observation that I have from x1. And then x3 based on x1. And so on and so forth. In fact, this is the underlying theorem of for a Bayesian network given a directed acyclic graph DAG. You're going to hear this word quite a lot throughout this talk. Given a graph, given a direct acyclic graph DAG, the joint density of this high-dimensional distribution are stipulated by this DAG. So if I have a DAG, that DAG can indicate that the joint density can be written as so-called factors, that xi represent ith coordinate of this high-dimensional distribution, and pa of xi represent the parents of the node I. So I'll give you an example. In this example that I started my talk with, so let's say that we are given this DAG. This is there is no cycle in it, like because you cannot go back, right? This is there is no cycle here. And so given this DAG, I can write the joint density as follows. As you see that I have 8 random variables here, and I can write it as set of factors. So this first factor would be x1 because it doesn't depend on anyone, and also x2. It also does not depend on any other random variable. And then x3 is dependent on x1, x4 dependent on x2, next line, and x5 dependent on x2, and x6 dependent on 2 random variable. And x8 dependent on x5, and x7 dependent on x6. So basically, given the DAG, we can read the way that the joint density or joint probability distribution, depending on whether it is the random variables are continuous or discrete, can be written as set of these factors. So it is of these factors. So uh, so the probabilistic graphical model can be a way to represent this factorization. So how to parameterize probability density, as I mentioned earlier, uh, having a DAG just tells you how the graph can be written as a factors, but doesn't tell you how to parameterize. So here I'm going to give you an example. So here I have six random variables, and I'm assuming that each of those can be 0 or 1. So in total, I have six random variables, and each of those can have uh, two possibilities. If I want to write this, if I let's say I don't know this probabilistic graphical model, this structure, the joint density between x1 through x6, if assuming no structure, needs the number of parameters for that would be 2 to the power of 6 minus 1. Of course, 2 to the power of 6 minus 1 because it should sum to 1. But given this specific structure, I can write the joint density as px1, px2 condition on x1, px4 condition on x2, and so on and so forth. So now the way to parameterize it, because x2 does not depend on anyone, I only have one parameter. I only need one parameter to specify it. This would be alpha, it would be 1 minus alpha. For the one that are dependent on one set of random variables, you can view it as a table that has what you are conditioning on. So here you're conditioning x1 and the variable itself. So hopefully you can convince yourself that because this is conditional, so this is basically representing p x2 condition on x1, it should the sum of the rows should be 1. So here I need beta 1 minus beta and gamma and 1 minus gamma. So the number of free parameters that I need here is 2, here is 1, here is 2 again, 2, 2. And here this random variable depends on 2. So you can view the parameterization. So this is basically representing this factor. And so the sum of the entire block um, should be 1, right? Um, oh, sorry, like the sum over this should be 1. So the number of parameters that we have here is going to be, for each value is going to be 4 of those. So as you see that we go from 2 to the power of 6 to very small number of random variables. So you can view a DAG as a way to reduce also the parameters of probabilistic, the general probabilistic graphical model. So one may ask that where this graph can come from. One way to create this graph is from known causal relationship between random variables. Another way is to represent the modular relationship between variables between that's known from prior knowledge. And also, it's also possible to learn this relationship from the data. I would like to point out that given a DAG and given Bayesian network, uh, presence or absence of the presence of the an arrow between two random variables does not necessarily mean causality. I'll explain that toward end of my talk. And DAG and Bayesian network is all about representing dependencies between random variables, but those dependencies does not necessarily mean causality. So in the following, we're going to dive a little bit deeper into relationship between DAG and independencies and that it implies. In general, you'll see three types of motif of a pattern in a Bayesian network. So one type of motif is when one random variable is represented by B is connected to two random variables. Of course, it's very tempting to interpret this relationship from causal point of view, but it's better to view that as a dependencies. So basically, the idea here is that if I know B, then A and C become independent from each other. For example, if I know the level of the gene B, the level of gene A and C are independent. There is also cascading events that like A is connected to B and C. So in this case, you can view it as if I know the variables of the B, if I observe B, um, knowing A does not help you, does not provide any external information. So an example is that given the level of gene B, the level of gene A provides no extra information on a value of the gene C. The third motif that can make interpretation a little bit more interesting is when two random variables are connected to one. And this is so-called V structure uh, in probabilistic graphical model nomenclature. And this is when A and B are not necessarily dependent on each other, but as soon as you see C, then they become dependent. An example of that is, for example, you can view C as whether my car works or not, like the engine of my car starts or not. So it's going to be 1 or 0. And A can be, for example, whether the gas tank is full or not. So 0 or 1, and whether my battery is working or not. So a priori, the gas tank can be filled or not, and the battery can be working or not. They have nothing to do with each other. But as soon as you see that the car is not working, you realize that either my gas is empty or battery is not working. So they're no longer dependent. So this is structure called V structure, and as soon as we observe C, they make them dependent on each other. So I mentioned earlier that there's a one-to-one correspondence between factorization bar graph and a set of independents. So for example, in this example, B is connected to A and C. And as I mentioned earlier, this implies the following factorization. I mentioned in the previous slide that in this case, if I know B and A and C become independent. So I'm going to prove it here that this factorization implies this independent and vice versa. So let's start with the left-hand side. So if I want to write PA condition on C and C condition on B, I can write it as PAB divided by B using Bayes rule. And if this factorization on the top is correct, I can write this as, well, it's basically PB and PB cancels out, and it becomes PA condition on B and PC condition on B, which basically means that A and C are independent given B. So now let's try to prove the other way. To prove the other way, we are basically saying that PA and C condition on B is PA this is by definition, and I can use Bayes rule to write this. If I so the same side here, if I rearrange the term, I'm going to get PABC PB PAB PCB, which basically is factorization. So hopefully I've convinced you that there's a one-to-one correspondence between set of independents that you see in a graph and the factorization it implies. Okay, as I mentioned in previous slide, um, we should be able to read the set of independencies from a DAG. So we call this IMAP, so which is represented as curly IG. G is the graph, the DAG, and I is the set of tuple that shows the independency. So what I mean by tuple means that, for example, you have some graph, and from this graph you say that these variables, this set of variables are independent of these variables if I condition on this one. So if this is x, this is y, and this is z, um, the Curly I map, the Curly I G I map is set of x, which is the idea of some variables, idea of some other variables, condition on another set. So one can define IMAP for a graph, set of independencies that are introduced by a graph. We can also do that for the probability density, probability distribution. The probability distribution over high dimensional distribution X, the IMAP of P is a set of independencies that are in this form. This is a set of variables, condition, and another set of variables. So the IMAP P is a set of, you can see it as like parentheses like this: X, set of variables, condition on this, and another set of variables. One question would be that, well, if I can read the set of independencies from the DAG, would that be the same set of um, independencies that are already in the probability distribution that are induced by that graph? And the answer to that is no, they're not the same. So let me give you an example. On the left, you see three graphs. The graph that two variables x and y are independent. So the set of Curly IG for this graph is that like x and y are independent, and this is empty, so you don't condition anything. And the set of independencies for these two is the same. Is basically the IG for these two is empty. It's basically empty. Now the question is that if I give two distribution, the distribution P1 and distribution P2, um, which of the following, these two graphs, allows for both probability to be distributed? I would like to pay attention a little bit into this distribution. Here, let me explain the notation. We have two variables, x and y, and here by x superscript 0 and y superscript 0, we are indicating that these random variables are binary, 0 and 1, and take two values, 0 and 1. So this is the joint distribution. This is the joint probability of both x and y being 0, and so on and so forth. So if you stare at these values for a second, you probably will realize that this is showing an independent probability density. Means that this specific instantiation of the probability density is representing xy, px, py, while this one does not have any specific configuration and any specific factorization. So if you look at these two, you realize that definitely this specific instantiation of the probability is consistent with this graph, but it's also consistent with this graph and this graph, because the way that this factorization is shown is basically any generic factorization. So this one, if I, for example, like want to write the factorization of this graph, this become x and y is px, p, y condition x. In fact, any joint probability distribution between x and y except this factorization. So this graph doesn't tell me anything. So this graph and this graph can represent both this probability distribution and this probability distribution. So why am I telling you this? The reason I'm telling you this is that the set of independencies that are induced by the graph is a subset of the independencies that might be in a specific instantiation of the probability density. So what is really informative in graphical model is absence of the noise, not presence of the noise. And when you have a node absence, you are enforcing a specific independencies. In this case, px and y are independent, while when they are connected, you are basically saying that there exists some parameterization that specific dependencies can hold. And so there is a notion of local conditional independence. Go back. Or local Markov assumption. So if you remember, I mentioned that given a DAG, we can write a full conditional distribution as a multiplication of the set of factors that looks like this: the random variables condition on the parent of that random variables. And based on that, we can define so-called local conditional independence. So the set of local conditional independence, although it may look a little bit mouthful, but it is actually very simple. So given a graph, the set of local conditional independence are basically a set of independencies that look like this: a variable, set of non-descendant of that variables, condition on a parent of that. So what do I mean by non-descendant? Consider, for example, this specific DAG. These set of variables are all descendants of this random variable. So if it is x1, set of descendant of x1 are all of these variables here. While, for example, here, these are not this. Well, okay, these are still descendant, but like while this one, it's not. So this one is saying that set of local dependencies, local independencies are a set. If you condition on a parent of the node, the node is independent all of these from all of these non-descendant random variables. So if you remember, I mentioned that the IMAP of the probability distribution are set of assertion that looks like this. This is a set of variables. This is a set of variables. It's also a set of the variables. And this is basically for a specific instantiation or specific probability density. So a DAG G is an IMAP of P if set of all local independencies that I mentioned earlier are the subset. So basically, there might be some independent set in a probability density that will not already be in here, but anything that is here should be already in the probability density. This is the example. This is probably very consistent with this example that I mentioned earlier, that the set of independencies that are created by the graph is some sort of like a conservative way of representing all of the independencies that might be already in the specific instantiation. So why is it important? This is basically to tell you this fact that I mentioned informally a few slides ago, that the fully connected DAG is an IMAP for any probability distribution. So consider, for example, a probability distribution between n random variables. So I can use this decomposition that apply to any probability density without knowing anything about the graph, and keep decomposing it. So I can condition x on x2 through xn, and then again I can decompose it into x2 condition the rest of variables, so on and so forth, and write it as this chain. And I can write that as this fully connected graph. In this graph, everybody is connected to everybody. Still is DAG, but everybody is connected to everybody. So as you see that I did not apply any specific factorization into this, any specific assumption into this factorization. So this is the most generic way of representing any probability density. And when you have a fully connected DAG, it can basically represent any probability density. So why am I telling you this? This is again to emphasize that in a DAG, absence of edge is what is important, which basically means that the absence of edge is more important than presence of that. I mean, in some sense, in a sense that like it it basically it talk about like the independencies that are in a graph. So one question would be that how do I infer the independencies from a graph? Okay, so I'm going to give you first formal definition. Don't worry if it's a little bit convoluted. I'm going to give an example, and hopefully with example, things become more clear. So let me give you a formal definition. If you remember a few slides ago, I talked about this, motif that you see in DAG. So one of them was like that, which I call it cascade. The other one looked like this, and the other one was um, was like this one. We call this one V structure. This graphic usually also called collider because two arrows collide on these random variables. So we call like we are looking into a set of statement like this: X and Y are independent of Z's, and uh, we want to see given X and Y and Z's are they, and given a graph, can we say that this is independent or not? So we say that um, uh, X Y X is independent of Y condition on Z if those are d-separated. What does it mean for three set of variables to be d-separated? It's kind of like a loopy definition in the sense that like they are d-separated if they are not deconnected. So what is deconnected? So let me read this formal definition for you, and then I'm going to give you examples. So given a DAG G, which is directed at a cyclic graph, and three sets of variables x, y, and z's inside of that DAG that are disjoint, so there is no node that are shared between x, y, and z sets, then x and y are deconnected if and only if there is no path there is no path um, if there exists a path that connects somehow x um, to y, such that all of the colliders that are like V structure like this are passing through Z. So basically what I'm saying here is that if we have a collider in that graph, that collider or one of its descendants should be in Z, and you have to somehow connect the path that start from X or start from Y and goes through Z. So um, if they cannot find such a path, then we can say that they are independent from each other. I admit that this definition probably may seem a little bit confusing. So let me give you examples. An alternative way of defining deseparation is as follows. If I give you a graph and I want to and I ask this question that x is independent of y condition on z, then um, uh, one way of doing that is to perform so-called moralization on a graph. So the moralization of the graph is basically procedure like this. The first thing is if we are interested, for example, in this original graph, and then I'm asking this question that does x independent of y given in z? So this is basically my question. One, so the procedure would be something like this. First, find the so-called ancestral graph, which means that like, I'm going to get rid of these random variables that are. So I'm going to look into set of all random variables that are ancestor of this graph. So I'm going to left with this, and then I'm going to remove all of these directions. So I'm going to get something that look like this. And because this is a collider, this is a V structure, see that there is an arrow coming here, there's an arrow coming here. You can view Z that have two parents, this node and this node. So this is kind of like they've been a little bit playful with the language that because there are two parents, but they're not directly connected. So this is kind of like an immoral graph. They have a child, but they are not married, so we're going to moralize it. This is what they call moralization, because they're married and they have children, they're not connected. It's moralization. Now you end up with a graph that is undirected, and it's undirected. And if you can find a if I can find you can find a path between x and y, means that then they are not independent from each other. They're dependent on each other. So in here, because of the moralization, I can find a connection directly goes from x to y. So how do I? So basically, in order to ask, this is the alternative way of uh, telling that if statement like this is correct. First, find the ancestral graph, keep only the ancestors, remove all of the arrows, and then moralize this graph. Means that like if two nodes have children, just connect them if they're not already connected. And then see if you can find a path between these two sets of variables. If you can, then they're not independent. So there is another way that I personally prefer this way because to me it's more understandable. If you remember, we talked about this tree motif and you always see that in DAG. So this is like cascade, collider or V structure, and structure like this. Comp. So one way to do that is basically if I tell you the following rules, then you can easily find that you can basically answer this question that if this is independent or not. So basically, rule is as follows: if you have a structure like this, it's like a cascade structure. If the observed random variable is in the middle, is going to block the path. So if you remember in the cascade, if I know the variables in the middle, it doesn't provide extra information about the other. So my path is blocked. But if it is not observed, I can pass through it this way. I can pass through it that way. If I also have structures that looks like this, um, if the parent variable is observed, neither I can go this way nor I can go this way. So this path is blocked. So, but if it is not observed, I can pass through both ways. And finally, if I have a V structure, if the V structure is observed, I can pass through it. But if it is not, I cannot. Also, another important thing is that if any of the descendant of this V structure is observed, I can still pass through it. So to summarize, this V structure is different from the other one because if you are observed, if that random variable is observed, you can pass through it. But if it is not observed, you cannot. While in the other one, if it is observed, you cannot pass through it. And the other things that you have to pay attention is that if any of the descendant of the V structure is observed, you can still pass through it. So why do am I telling you this is that if somebody asks you a question that like given three random variables or three sets of random variables, are they dependent or not, then you can follow these rules and then you can view Z as an observation. And if you can find a path between X and Y, then they are not independent from each other. So let me give you an example. I don't know why it's not going to the next page. Okay. So given this graph, the question is that if A is independent of E, condition on B. So this is B. Now the question is that like, can I go from A to E? So if I want to go from, this is E. So if I want to go from A to E, because this is not a V structure, it's more like a cascade structure. This is more like a cascade structure. I cannot pass through it because this is blocked. So the answer to that is no. Let me give you another one. Now here we are asking that if A is independent of E, conditioning on C. You see that we have a V structure here. C is a collider. So because it's the V structure, I can pass through it. So I can start from A, This is not observed, I can pass through it. It's a V structure, I can pass through it. And so this is the V structure. So here is a V structure, but I'm not coming from here, I'm coming from here. So I can pass through it. So I was not able to go through this path because this V structure is not observed, but I can go through this path. So the answer to that is yes. Now the next question that we should answer is that is all you need for causal inference? So in fact, it should be questioned like this: is DAG all or Bayesian graphical model, a Bayesian neural network? Sorry, is a Bayesian network is all you need for causal inference? Hopefully by now, given what I told you already, hopefully you have some idea that like it's probably not all you need. You need something more than uh, uh, Bayesian network for causal question. So let me give you an example. So let's say that this is the IMAP of the G. So and so I'm looking for a graph that satisfies the set of independents as follows. If I condition on X, a condition on Z, X and Y should be independent. Now the question is that which of these three graphs satisfy this condition? This is the V structure type. This is more like a common cause type of structure, and this is more cascade from X to X1 to X2, and this is the other way around. Now, and we are asking this question that this set of independence is consistent with which of these three graphs? So let's start from graph C. So given this graph C, I can write it as the joint density as follows. So this is going to be X2 condition on X3 and X3 condition on X1 multiplied by X1. This is a representation that's coming from graph C. So so if I start from here, I can start manipulating the factors and see what I can get. Okay, so I can absorb this term into the term in the middle and get this term here. See if we can remove this. So I can absorb x1 into the second term and get the term in the middle and use the Bayes rule to rewrite that. So because px2 condition x3 can be written as px2 and 3 divided by px3. So now if I have this term, I can write this one as px1 condition x3 using Bayes rule. So I'm going to get term on the right hand side. And of course, I can simply use the chain rule, and the chain rule is that this term is the same term, and this is just using the chain rule. And suddenly you see that this is the structure that's coming from the graph D. So in the graph D, we have px1 condition x3 and x3 condition x2 multiplied by x2. So you see, and also so similarly for graph B. So this set of independence, is consistent both with graph B, graph C, and graph D. So why am I showing you this set of equivalence? Because I want to tell you that if there exists one causal graph, then not all of these should be correct. So one of them should be correct, not all of them. So while conditional independence uh, can be consistent with not only one, but three types of the graph. So for these three types of the graph, the set of conditional independence are the same. While if there exists some real causal structure, that real causal structure is one of them. So this is this is I show you this slide to tell you that in order to perform causal inference, you need something beyond just conditional independence.
Okay, as I mentioned earlier, for causal analysis, we need to go beyond just Bayesian network. We need a causal DAG. So consider this case. Um, we have 5 random variables: season, whether the sprinkle is on or not, whether the rain is already rained or not, whether the pavement is wet, and if it is slippery or not. So we need to have a causal relationship. We need to construct the graphical model in a way that it represents the causal relationship between that. So the sprinkle is more likely to be on if it is in a hot weather rather than a cold weather, and also the season influence the chance of raining, and both of them jointly influence the wetness of the pavement, and the wetness of the pavement directly influence the slipperiness. So what is different in causal DAG versus the typical Bayesian network is that we can apply intervention. This is what is called do operation in causal analysis. So let me give you an example. So if, for example, an example of the intervention is, in this case, would be turning on the sprinkle on or off. So if I turn the sprinkle on, it really doesn't matter if we are in a cold season or we are in a hot season. So effectively, if I intervene in the sprinkle status, it makes it independent of the season. So effectively, the do operation on X3, which represents a sprinkle, disconnects the status of that variable from the season, because it really doesn't matter if I intervene. It really doesn't matter if it's winter or summer. So not only it changes the status of the variable, it also makes the modification to the structure of the graph. And also, if I intervene, there's nothing probabilistic about it. The probability of X3 being on is 1 because I went there and make sure the sprinkle is on. So you can view this do operation as changing the status of the random variables in a graph and disconnecting it from all of its parents. So if we have a causal graph, the graph that represents the relationship between variables in a causal way, we can do the following things. Of course, like any graphical model, we can perform prediction. An example of the prediction would be that if we observe the sprinkle is off, what's the probability that the pavement is slippery? So there is no intervention here. So this is a typical question you can also ask from Bayesian network as well. But what is different here is that we can do intervention. So intervention is that if I make sure that the sprinkle is off, what is the probability of the slipperiness of the pavement? And this is different from the graph. This is different than observing that the sprinkle is off, because here you make a modification not only to status of the sprinkle, but also make modification to the structure of the graph. Also, another interesting question that you can ask if you have a causal graph is so-called counterfactual. So let's say that you wake up in the morning and you observe that the pavement is not slippery, but the sprinkle is on. So now you want to ask this question that, okay, so now I know that the pavement is slippery. If I want to know the effect of the sprinkle on that, I have to basically ask this question that, like, would this pavement be slippery if the sprinkle was off? So this is a counterfactual question. We are living in a world that sprinkle is on and the pavement is slippery, but we want to say that, like, if this is the effect of the sprinkle, would it be the same if the sprinkle was off? So this is the counterfactual question, and hopefully in the other session in this tutorial, we'll see some examples of that in our domain as well. So after all, so we said that we need a causal DAG. What is the difference between causal DAG and a typical Bayesian network? So one of the properties of the causal DAG is that like, so the example of the causal DAG is this two graph that I mentioned earlier. So the first property is the same property that Bayesian network has. Given the network, that has like, V represent all of the nodes of this network, and X is the one that we are intervening on. So we have to make sure that the set of independents that the graph indicates are the same as the one that you have in the graph in the probability. So basically, it says that the graph and the set of probabilities should be consistent. The second one is the operation of the do that I mentioned earlier. If you intervene on a node of the graph, you basically setting the probability of that graph to 1 regardless of the status of the pattern. This is basically saying that if the set of the variable is in a set that you are making intervention on, the probability of those will be 1. Of those variables will be on. And finally, it says that if the variable that we are intervening on is not in a set that we are making intervention, the probability of the new graph that we are making intervention on is the same as the graph before. So the third statement basically says that if the variable that you are intervening on is not within the set of intervention, it just follows the structure of the graph that you have already stipulated. So, but in reality, although it's easy to make an intervention on things that are like sprinkled, it's easy. There is nobody gonna get hurt. In the real world, especially with medical data, intervention is not always possible. It can be unethical, it can be costly, or it can be impossible. So the causal analysis from observational data is effectively what we want. So we want to see what kind of causal question that we can answer from observational data, knowing either the causal structure or partial knowledge about the causal structure. So one of the most important things to answer is identifiability. So basically, the question of identifiability is that are we able to, if we perform the do operation, let's say that we are able to perform the do operation and we change intervene and make sure a variable, so here is X, is actually changed. If I have two models that follows the same graph and we have the same observation between these two graphs, do they produce the same causal effect? Put it more formally, the causal effect of the action on X variable and observing the effect on Y would be is identifiable if you have two models, basically the model M1 and model M2 that both follows the same graph. And if the effect of observation here, the observation is Z for both of them, and the effect size that you are interested in is Y. If we perform the operation of changing X is the same, the causal effect should be the same. If this condition is satisfied, we say that the causal model is identifiable. The reason that we should care about it is that we are interested in observational, in performing causal inference from observational data, and we want to ensure that it is possible. If it is not identifiable, then basically our hope is lost. We won't be able to answer this question from observational data. And the second important criteria is a backdoor criteria. So let's consider we are given a causal graph G, treatment X, and effect Y. We would say that a set of observations Z's are backdoor, satisfy the backdoor criteria if none of the variables in a set Z are descendant of X. So if this is X, this is Y, so Z cannot be here. It was descendant of X, or it cannot be here. It should be it should not be descendant. And also, every path that goes from X to Y should be blocked. So for example, it cannot be something like this. So it cannot be something like this, because if this is observed, there's the Z is a collider here. There's a V structure here, and the path from X to Y is not blocked. If these two criteria are satisfied, the Z is not a descendant of X, and it blocks all of the path going from X to Y, and then we can say that this do operation, that's a result of intervening into X, can be done through this marginalization. The reason that this is important is that there is no do operation on the right hand side of this equation, and that means that we can perform this from just observational data. So let me give you an example of this. So for example, if this is the causal graph and X is our treatment and Xj is our effect, if X3 and X4 are in Z, so we want to check if these two are observation, the rest are unobserved. This is unobserved, 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 unobserved. Is there any, is the path blocked? So here is an example. So if I want to go from X to Y, I cannot go this way because this is blocked. I cannot go this way because this is blocked. So what about here? So I can go here. I can pass through here because this is the V structure. See that there's a V structure here. And if I want to pass through, this is blocked here. So this set satisfied the backdoor. And hopefully you can do it on your own for X4 and X5, but you can see that there's a symmetry, so that should also satisfy. So let's do it for X4. If I can erase what I wrote. So what about X4? For X4, I cannot go from this path because this is blocked. But what about this? I can pass through this because of the V structure. I can pass through this, and I can go here. So this does not satisfy the backdoor criteria. That means that if X4 is the only variable you observe, you cannot do. It doesn't satisfy the backdoor criteria, and you cannot perform that do operation just from observational data. And finally, I started this presentation with this graph that I told you. And one question that we didn't answer throughout this talk is that where these graphs are coming from. And we assume that we are given a graph. Either it's coming from prior knowledge or it's coming from some experimental data. And we have this causal question. But what if you want to learn it from the data? So let me give you an example here. So in this example that I told you, that we have number of Nobel Prize for each country and an amount of chocolate consumption. Can we answer this question that if X is causing Y or Y is causing X? I mean, it goes without saying that in this specific example, neither X causing Y and nor Y is causing X. In fact, there is a hidden factor that causes both of them. But even in a case that somebody tells us that, look, there is no hidden confounder here, even in that case, answer just based on observational data. So let's say that we have another data set that this is X and Y, and this is our observation. This is our observation, and it passes through this. Can we answer that like X is causing Y or Y is causing X? Can we answer this question, assuming there's no hidden confounder? So in this case, let's assume that X is causing y. So x is causing y, and the model is, let's say, really like it's linear. So y is beta x plus some noise. So in this case, effectively we are assuming that the noise is added like this. So if I compute the residual, these are IIDs. So I won't go through the detail, but even okay. So if it is other way around, if it is then x minus. So in that case, the noise is really added like this. But we don't know which one is which. We don't know the noise. This is the noise or this is the noise. So now the question is that which one is causing, so in this case, y is causing x, and in this case, x is causing y. So can we answer this question just based on this observational data? I won't go through the detail, and I'm happy to provide references. It turned out that even in case of two variables, we can only answer this question that x is causing y or y is causing x only if this residual is non-Gaussian. And there's a paper by my colleagues Kung Zhang that explain why is the case. You need in this case for noise to be non-Gaussian in order to answer this question, assuming that there is no hidden confounder. So I'm going to end this section of the tutorial. My colleagues will continue, and hopefully we have provided enough background that makes this field of research exciting for you. Thank you.